Right. So guys, I'll look like this where the few guys are. Right. So are you okay with switchboards? Now guys, one of the good things when it comes to switchboards, if you got ASNZ 3000 with you, it's chapter 2.9. Everything about switchboards is in chapter 2.9 or 3000. But let's go through some of the stuff which is important. Now you all know what is the voltages we use in New Zealand. It's a bit of revision. Do you all agree? Generation, where they generate electricity. Transmission, and when it goes from point A to point B along the motorway. And distribution when it comes to our houses. In distribution, we work with 400 or 230 volts. Now that secondary side of that transformer is called the MEN system of supply. Regulation 727 states very clear. Right, and there is regulation 27. In regulation 27, it says the first switchboard must be a MEN. Where must it be? Electrically closest to the point of supply. Switchboards. So, they can ask you a regulation question on switchboards. They can ask you a 3000 question on switchboards. You all agree? Regulation 27, ASNZ 3000, chapter 2.9, all about switchboards. Now, in 2.9, it tells you where to put the switchboard, how high it must be, how low it can be, what's the IP rating of it, etc., etc. Now, when you look at this one, what do we call the first switchboard after the supply system? Is it a DV or a MEN? DV. What do we call the first switchboard after the transformer? MEN. Always MEN, right? Now, guys, where is the first switchboard? Closest or anywhere? Right, it says electrically closest. Go back. Read that number B. It says electrically closest. So you put it where your cable will be the easiest to use. It doesn't have to be physically the closest, but electrically the closest. So if your cable comes into the house, underneath the floor, concrete, and the only place it comes up is just other side the door, that's where you'll put it. Make sense? Electrically the closest. Right, guys? Also, the part which is flickering now, what do we call that first switchboard? MEN or DV? MEN. MEN. Right, now, what type of transformer is that? Delta star. The secondary side must be star in New Zealand. I don't care what the primary side is. But from that, what type of switchboard is that? MEN or DV? Now, gents, unfortunately, ladies, there's no physical place in 3000 where they say in words, what are the switchboard you must use? But in 3000, chapter number 5 about earthing, there is a very similar board. But before I do that, switchboard A is a single phase or three phase or two phase? Right. You all agree? That one has got all MENs. Go back. First one, number A, is a single phase MEN switchboard. You guys agree? The second one is a two-phase MEN switchboard. The third one is a three-phase MEN switchboard. You happy? So guys, the star part and the transformers, this part I'm circling now, is called the MEN system of supply. TNCS system. Right? It means we supply within phase, supply within neutral. Sorry guys, you have to create your own earth. Put a whacker peg in the ground. Right guys? 3000, page 215 or 5x3. You'll get a switchboard drawing similar to this. Now, one thing I'd like to share. If your supply is here at the top, what do we call that first switchboard? What does the regulation 27 say? It must be a MEN. Does that represent MEN? Right? Well done. Can a MEN feed another MEN? Yes. Yeah, nothing wrong. Right, I'll just give you a bit of a thumbs up hint. In the regs, no, in the 3000 book, it says if you've got an outbuilding, you can only have one MEN board in it. But when do you have to install a switchboard in any building? when the current is 100 amps or more. So if you've got a house and a garage and they're separated, you happy with that? When do I have to put a switchboard in the garage? 3000 says if the current going to the garage is more than 100 amps. Otherwise, I can run a TPS for the plugs, TPS for the lights, that's it. It's the extension of it. But I know you guys are clever. You put a little switchboard in the garage, hey? Nothing wrong with that. Now that garage switchboard, can it be MEN?
Yes.
But then you have to whack a peg in the ground and put a link in between. Or you make it a DB. And the DB is just no link. DB is no link. That earth comes from the MEN board. Right? That peg in the ground, that whack the peg in the ground. It doesn't have to be a peg. It can be a pipe. It can be a reinforcing. It can be concrete. It can be the structure of the building. 3000 mentioned all that lovely things for us. Now, guys, you all agree that an MEN can feed a MEN, or MEN can feed a DB, can feed a DB, or an MEN can feed a DB. Yeah. Next week when we do testing, I'm going to show you why there's no link between neutral and earth. Yes, one, and also the earth here is not allowed to carry operational current. But if you put a link in, there will be operational current. Right? Now, the MEN system, that peg which is on the ground, do you all agree that that peg must be connected to the earth bar? With what type of conductor? You all agree a main earth conductor? The main earth conductor can be anything between 4 mil and a 120 mil. You based it on the main active coming in. Right, guys? That's enough for you on switchboards. But wait, there's a little bit more. Why do we earth the neutral? Why do we put a link in the first one? Gentlemen and ladies, if you don't, you could have current flow through the earth back if there was an earth fault. In other words, there's no link. And also, you do not guarantee a parallel path if there's a fault. And number 3, the current, because of the fault, might be so low that it will not blow the breaker or trip the breaker. And thirdly, if you don't link it, you might have a potential voltage between neutral and earth. That's why, if mommy touched the sink, she might get a bit of a shocking experience. All right? Be careful. That's just nice to know stuff. Right, guys? What type of switchboard looks like that? MEN or DB? Which type of switchboard is that? So, guys, here comes a question in the exam. What do you call the wire between the earth peg and the earth bar? Is it is it a main earth conductor, a bonding conductor, or a protective earthing conductor? Right. What do you call the wire between earth bar and a water pipe? Right. Bonding conductor. And guys, all your answers is here. Can you see on that picture? What do you call the wire between earth bar and the socket earth, which is inside the cable? As a protective earthing, bonding, or main earth conductor? That's it. We only have 3 earths. There's no other earths in this country. Oh, by the way, there is one, but we're not working with that a lot. We call it a functional earth. Right. And last thing I'd like to share, your main earth wire and your bonding wire must be a wire which runs by itself. You can't have it inside a cable with other active conductors. You guys with that? Right. From your earth peg, correct. Because your earth peg, your main earth wire, not your earth peg, your main earth wire is an extended earth bar.
Yeah, well, sometimes you see pipes on the stairs sometimes.
Yes. Now, the law has changed in 2003, where you can extend the wire from where the clamp is to a water pipe. That's all what it says now.
Why the DB is not connected, where there's no link, the neutral and the earth?
Sorry, repeat that again.
Why there is no link in the DB?
Because
earth neutral.
Okay, I'll show you now. If I bring in earth to earth bar, 2 screws. If I bring in link, 2 screws. If I bring in my neutral, 2 screws. You all agree with that? Yeah. Right? Now, active comes in, and then you can loop it to the other parts. And can you see that this 2 circuit breakers is fed from that RCD? Now guys, every RCD has got its own neutral bar. So this neutral feeds that one, and this neutral feeds that one. So we call this the protected RCD neutral. So this neutral bar is for that 2 breakers. You guys happy with that? Correct, and I'll show that very shortly as well. So guys, to carry on, you all agree, 1 RCD, 2 neutral bars. Main neutral, RCD neutral. Happy? Right. Now, look at this one. This is a DB. Right, guys? Where is a DB fed from? MEN board. Did you hear that? Jesse?
Yeah, I
This
heard that.
distribution board comes from MEN board. Earth comes in, neutral comes in. No link. Because if 10 amps flows in the phase, how many amps flows in the neutral? 10 amps. How many amps flows in Earth? 0. But if you put a link in, and that's 10 amps, then 5 and 5 goes back. This Earth now carry operational current. And 3000 says in the testing, the Earth is only allowed to carry fault current. That's why a DB is not allowed to have a link. Make sense? Cool. Right, the wiring's the same. Right, guys, I want to ask you a question on the next one coming up. But can you see it's the same wiring? Look, guys, in the olden days for 10 marks, they ask you to draw that. Now they ask you questions on where is the RCD's neutral fed from? Then you're going to say from the main neutral. Where is the RCD neutral going to? To its own neutral bar. Where is the main breaker fed from? Well, obviously from the cable coming in. You know, so they ask you now questions on what it could have been if it was a drawing. Now, guys, you find out that in my book I wrote, there's questions on switchboards where I ask you, what do you call that bar? What do you call that? What do you call that? What do you call that? Can you see they can ask you that? So I call it A, B, C, D, E, F, and you have to tell me if it's an earth peg or this or that, etc. They can ask you questions like that. Right, look at this one. Right, technical question 1. How many RCDs are there? How many neutral bars are there? 3 or 4. Remember, each RCD's got its own neutral plus the main neutral. There's a MEN switchboard. What is between the main neutral and the main earth? There's 4 because there's a RCD's neutral. So remember, each RCD's got its own neutral, and then you got the main neutral. But they were classified as a neutral. So no, each individual hole. That's why there's at least 2 or 3 little ones here. So what I want to share, I'll show you guys now. Each neutral, if you put a little bar here, it represents the same as that one. Right, this switchboard. Do you all agree that the main earth, your main neutral, and your MEN link has got 2 screws? Right, it says that. But it also says a little other thing, that if the screw which goes in the hole covers the hole more than 80%, then it only needs 1 screw. So you can go and read that before you go to bed one night. That's more a regulation question. But my question is, do we put a tag in the switchboard? Yes. If you find that in the 3000 book, I buy you a blue label whiskey. It's not there. It says you must identify it. Doesn't say how. But how do I identify there? Have a look at the amount of screws. 2 screws.
So
now,
another way of identifying it.
Where do we put a tag? You put a tag on the peg if the earth can be disconnected with a clamp. If it's CAD welded, then you don't have to put a new tag as well. But guys, Marius always say, be safe, be kind. Put a tag there. Regardless, you will always be good. Now, the supply comes in. There could be 2 breakers, which is not an RCD, and each one feeds. Now, guys, look at this RCDs. Can you see that each RCD is polarity conscious? In. Now, can you see that the bottom part goes out, the bottom part goes out, and the bottom part goes out? Now, do you all agree that all the earth is from the earth bar? All the non-RCD protected neutrals is from the non-RCD protected neutral bar, and each RCD subcircuit is from its own neutral bar. So each neutral is fed from the main neutral, and each one feeds its own neutral. And then obviously we just add the subcircuit. Happy with that? So guys, when I ask you a question about switchboards, think practically what you will do. All right? Happy with that? Right. 3 RCDs, 4 neutrals. Now I'm going to zoom in. Yeah. See that neutral bars? I'm going to zoom in. Is that what you guys talked about?
Yes.
That is also a neutral bar. But 3000 says the reason I put 1 neutral per each one is because it says when you remove a neutral, you do not disturb others. What does it say that? Each one has got its own neutral conductor. Now, when you look at this, can you see that this RCD, there's 3 breakers? First breaker, first one. Second breaker, second one. Third breaker, third one. Got it? Come on, if you do this, you're a bloody good Sparky. I don't say you're not, but it will be even better. Right, guys? Are you okay with switchboards?
Yeah.
Right. Let's hit semiconductors. Last topic for the night. Yeah, and the protection. On that video on protection. But we're going to do it next week when we do testing again. Earthing, we did it. It's everywhere. It's part of testing. It's part of switchboards. It's embedded throughout the whole syllabus. But when we do testing, we're going to go through all that. That's next week. Right, guys, semiconductors. Now, a lot of you guys hate it, and some of you guys love it. There's no in between. Unfortunately, there are questions you will get in the exam, and unfortunately, there's questions you will not get in the exam. I don't know, so I'm going to make it as possible, and everything I'm going to show you tonight has been asked, but depends how they ask it. And you will not get all these questions. There's no way that you're going to get 30 marks on semiconductors. Firstly, you must know your symbol. What type of symbol is that? Does anybody know? A diode. Right, a diode. Right, guys, a diode. See, diode. Right, guys, one good thing is they will give you 4 answers and you have to choose it. Now, what is that? It's a diode with 2 arrows.
Zener diode.
Right, guys, that's FTB. A light emitted. Look, it emits away. But what is this one? It comes towards you. A diode. No, it's called a photodiode. In other words, sunlight shines on it, and the diode will then switch on or switch off. Oh. Have you guys ever seen a daylight switch?
Yeah.
That's inside the daylight switch. All right. Right. What about this one? Ooh. Is that a diode, an LED, a photodiode, or an SCR?
ACR.
So guys, a SCR stands for silicon controlled rectifier. Now, a SCR is like a diode. The only difference is the gate needs to be pulsed before it becomes a diode. You need to pulse it. The other ones works with the voltage. Right, we're going to cover all this again. This is just a bit of a, let's see what are the definitions. What type of definition? What is that?
Zener.
Is it a Zener? Yes, it's a Zener. A Zener might have little arrows or little straight lines. It all depends. But that is the average diode, a Zener symbol. Right, you'll find out that all the symbols is in my workbook and my handbook. Right, guys, what is that?
Triangle.
A triac. Well done. Tri means it is a SCR in both directions. Now, if I go back one, you all agree that that arrow shows from left to right. Left to right only. So we will call that DC circuits. It can only flow one direction. Now look at this one. Can it flow both directions? This is used in AC circuits. So if you say that is a triac, two diodes in both directions. So that one is a SCR in both directions. That one is a diode in both directions. Right, what is this? It's a transistor, but what type?
NPN.
Right, I'll give you a hint. See that arrow there? It's always where the N is. So it's NPN. So in the exam, guys, they're going to give you the symbol and they're going to ask you what it is. Yes, an NPN transistor. And obviously the arrow shows in, that's a PNP transistor. So your arrow always shows where the negative is. Right, the transistor is an amplifier. What is this? Is it two capacitors or a battery? Battery cells. Two cells. Right, what's that? Ooh. A coil or inductor. Right. Can that represent the coil of a motor? Yes. Any coil which needs electricity. Can that be a ballast? Can that be a coil for the lights? Yes. Right. Now, guys, if you put an arrow through it, it's called a variable inductor. So anything with an arrow through it means you can tune it to change the inductance or the resistance or the capacitance. Right, guys, what is that? It's some type of transformer. Yes, well done. As you guys can see, the giveaway is the center point. The point where the common is. That is a center tap transformer. Right, guys? Can you see there? Center tap. If you have 230, the total is 460. Right, well done. I know this is small, but what do you call that one? Yes, can you see there's a common one? We did that last week. It's an auto transformer. Well done. And gentlemen, ladies, all the symbols has been asked by different people in the exams. So you just have to go and play with them. Right, guys, the next one coming up, you can't see it very nicely, it's a transformer. That one with a little line through it is a thermistor. Now you get two types. You get one with a positive and one with a negative. It means as it gets hot, it changes, or as it gets cold, it changes. Now the one with a P or a positive on it is normally inside your car's radiators. So as the water gets hot, what goes on? The fan. What is in your fridge? A positive or a negative one? Negative. Right. So that's a thermistor. Right, guys? That little block is called a. Right. Another example of a resistor is a zigzag. Boom, 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 boom one. Not curly, curly, curly. Right. The arrow through the resistor, variable. Variable resistor. Right. What is that, guys? A resistor split in two? No. It's a fuse. Have you guys seen that before? Capacitor. Right, guys? Some capacitors got a straight line and some don't. But what they did, they made it a curly line because that would be positive and that could be negative. But it doesn't matter, it's a capacitor. What is that?
Variable capacitor.
That's good. It's a variable capacitor. Right. Now what is that? And that's a bit small. You all see that's a bridge rectifier? It converts AC to DC. Well done. What is this? Two circles? Transformer. Sometimes they put a little triangles in here or stars in here. Yes, so instead of using this ones, the only difference is that it's just another transformer symbol. Then normally what we do, we put a triangle or a Y in here, and that represents a star on delta three-phase transformer. What is that one? No, delta star. Right? Delta star. Now guys, what is that? Right, that is a CT or a current transformer. Now gentlemen, ladies on board, please make note. You're going to get at least 5 of them. I don't know which 5. I hope all of them. Is that hard, guys? All what you need to do for the next week to go through this and practice it. That's all. Ask yourself. Yep. Well, the good thing is they're going to give you all 4 answers. And one of them is correct. 3 of them is, sorry, 1 is correct, 3 is wrong. You must just choose the right one. You will not believe the ones they always ask. They ask transistors and up So from the transistor up is the most common ones. All the diodes and the 2 transistor ones is the most common ones. And the CT one, the last one. They are very popular. But guys, unfortunately, they can ask you anyone. All right? Cool. Now, there is a symbol of a diode. You all agree that current will flow, if you look at the symbol, from left to right. Now guys, I don't know if you guys can see. Can you see that that's a line and it looks like a K? See that? Line and a K. So that's your cathode. There's your anode. Current goes in from A to K, alphabetical. In, out, anode to cathode, positive to negative. So if current flows through the diode, we call it forward bias. If the current goes back, we call it reverse bias. So try again. If a diode works, it's forward bias. If a diode don't work, it's reverse bias. Now they're going to ask you this in the exam. They ask you, when the diode operates, is it forward bias or reverse bias? Forward bias. It's forward. It moves forward. It goes on. It's easy to remember. Reverse bias is it cannot operate. Is that okay with everyone? Right. Around about 0.6 of a volt, we switch the diode on. Now, at 0.6 of a volt, it becomes conductive. But if there's no voltage, it's not conductive and it will not operate. Right, guys, where do we use diodes? Yes, but is a diode used for rectification or is it there for switching on lights? It normally gets used where you want to allow current to flow in one direction, and if you add that, if you put an AC wave in, current will go in and it can't come back. And I'm going to explain that to you. Very simple. Round about 0.6 of a volt, we'll switch on a silicon diode. Round about 0.3 of a volt, we'll switch on a germanium diode. Now here comes the part. A diode in a water term is a non-return valve. Current will go in, but it can't come back. But have a look at this one. 0.6 of a volt will switch the diode on. But when it comes back, it will be able to stop. How many volts? Look there in the left-hand side. Around about 400 volts. So it allowed current to go in, but voltage not. So it stopped the voltage in the opposite direction. Now I'm going to put that there in a much better picture. So if I give you a diode, will the load work? Yes or no? Have a look. Will the load work? Does current flow through the diode? Does it flow through the diode? If you have a look, I'm going to put my mouse here. Positive to negative. Positive through the diode. Does it work? Is this forward bias or reverse bias? Forward. Now look at the reverse bias. I swap the diode around. Current goes in and gets stopped. Look there. It's off. It can't work. So that diode is now reverse biased. It stopped that circuit to work. But look, it's a DC circuit. Now I'm going to change it to AC. See the AC? Current goes in from phase through the diode, through the load to neutral. In a reverse option, it goes from neutral through the load and stops. You see it can't go in. So input waveform, output stops. So it's in, stop, in, stop, in, stop. So we call that pulsating DC. Now guys, very important. The diode that way is forward biased. Back is reverse biased. So input waveform, AC. Output waveform, pulsating DC. Can you see it stops all the bottom part? So to give you an idea, it goes in, that part there, it goes in. When it comes back, it's that part there, opposite direction, it stops it. That's why there's nothing. Then it's in again, nothing. In again, nothing. In again, nothing. So you put 50 hertz in, you get 50 hertz out. Now, what voltage can you put between phase and neutral? Have a guess. 230. How much volts are we going to get across the load? It will drop, but you have to know this. It's not on your formula sheet. Firstly, when we talk electronic devices, we talk about volt peak. Now, if I give you RMS, what is volt peak? How do we work that out? Is it a little bit more than 230?
Yeah.
So we divide that by 0.707 and we get 325 volts. That voltage is called volt voltage. So guys, capacitors. That is your RMS voltage. So people with thick glasses and more like this, they work out that we only use 230 volts. We don't use 320 volts. 325 is around the cable. Inside the cable is 230 volts. If you want to look at that.
It's always 0.779.
0.707, always.
Yeah.
So guys, 325 volts is your peak voltage, always being used by electronic stuff. Electronic stuff use peak voltage. We only use RMS voltage, which is 230, 230, 230, 230 to earth. Got it? Now, have you guys heard about 0.707? Have you guys ever heard about 0.636 or 635?
Yeah.
Average.
Yeah.
We want to work out what's the average voltage. So what you do, you take the average voltage of 0.637, but because you only have half the wave, you're going to get 103 volts. So that is the voltage you measure on the other side. Now that voltage you measure is DC pulsating. So in a slow motion action, your meter will show 103, 103, 103, 103. It will flicker. But how many times will it flicker, guys? How many percent hertz? 50 hertz. So you will see no difference. So, to recap, this side, 230 volts. That's what you measure with your multimeter. But volt peak 325. Because you took half the wave out, you divide it by half. So if you take that half away, then if you multiply 325 with 0.637, you get 206 volts. And I'm going to explain that to you. So firstly, if you put one diode on mommy's hairdryer, it goes from very fast and then second speed through one diode. From 230 volts, okay, 325 volts peak, or as we know it, 230 volts, right? And you go to slower speed, how much volts are going to go through the hairdryer? 103 volts. So there we drop the voltage with one diode. If you go to all this cheap equipment, speed control, they put one diode in. There is the cheapest speed control you can get. Got it? Let me explain it to you in another way. If I give you a center tap transformer, do you agree that it will go that way or that way through the transformer? No. With a center tap, if you put in 230 volts, the transformer will drop the voltage down. I'm not worried about the drop on voltage. What that two diodes do, it is a rectification when you put AC in and you get ripple DC out. So there you see two waveforms. See that? So the diode will stop one, stop one, stop one, stop one, but together the load will get a DC ripple. Not pulsating, but ripple means all the way. Right? Now, the voltage you're going to measure across that load, it all depends on the transformer. So that is not a very easy explanation, except if you put 230 in and you got 230 out, that load will not be 230, but run about 200 volts. And I'm going to explain it to you now. If you put 50 hertz in, you get 100 hertz out. Because for every little top notch, it's 50, 50, 50, 50. So that is 15, 50 is 100. 15, 50 is 100. So one sine waveform is 50 hertz, but if you swing both to the top, you get 100 hertz. That is an exam question. But now here is the one you all know. Have you seen this before? Have you all seen full wave rectification? I put 50 hertz in 230 volts. Operation is, follow with me, P to diode 1, to load, to diode 4, neutral. You agree with that? It goes in P through diode 1, through the load, through diode 4 to neutral.
That's full load.
Yes. This is full load. This is full rectification.
Yeah.
Right, are you all agree with that? So one other thing I'd like to share here is if you put 230 volts in, phase in through diode 1, through the load, through diode 4, there's your first wave. Now the opposite is the opposite direction. See that opposite? It goes into neutral, through diode 2, through the load, through diode 3, back to phase. You see that? So current goes from phase to neutral, then from neutral to phase. But every time it goes through the load, the same direction. That's why whatever you put in AC, you get ripple DC out. See that? If you put 50 hertz in, how many hertz you get out? 100. 100 hertz. Remember, if you do that, that is 50 and 50, give me 100. So there, that is 50 cycles. You only look at the top part. It's 50 of them. There you get 100 of them because it doubled. Right, now here comes the part. What is the supply voltage? 230. What is volt peak of 230 volts? I just told you. 325. You guys happy with that? I would like to know what voltage am I going to measure here. So what you do, you take the 320. You want to work with the average voltages. You take your 325 and you multiply that with 0.637. And gentlemen, ladies, 0.637 is a standard. It's a 0.707 has been pre-calculated. 0.637 is also an average standard. When you multiply that with each other, you get 206 volts. So guys, if I measure 230 here, I'm going to measure 206 volts DC ripple on the other side. Now, you'll find out that in my handbook, if you've done it, you'll see that I've also asked you what is the voltage. If you put AC 230 in, what is the ripple DC voltage? Now, guys, the chance for you to get a question like this might be 1 or 2 questions. And guys, if you struggle with this, A. Try something. Don't leave it blank. Right? So guys, if I put 50 hertz in, how many hertz do I get out? 100 hertz. Happy with that? Go. Right, guys, have you ever seen a bridge rectifier like that? Which is the same like that one. You guys with me? Follow my arrow. Current goes in with phase. Do you all agree it's going to go through that line there? Yeah. Then through the load. Then through that diode there. And then back to neutral. Have you seen that before? Then the opposite direction, it goes in neutral. Up through that one. Again through the load. And all the way back to that one. You guys happy? Now, will that diode work? Follow my mouse. It goes in, down. Oh my golly, what does that diode do? Stops it. Let's try this one. Current comes in. It goes through, around. What happens there? You see it stops it again? Right?
No.
Right. And look at this one. Current goes in, around, through to neutral. Woo! The first one works. Let's throw back. In, through, yes, through, yes. Yeah. Gentlemen, ladies, you will get one of them in the exam. Yeah. Did you had one before? Yeah. Right, guys, does that make sense? So all what you need to do is to know if you put phase in, you get ripple DC out. 50 hertz in, 50 out. I'm going to ask you guys again. See there, it goes in through that diode to this load, through that diode and back. And neutral is the opposite direction. Now guys, go and practice this, listen to this video again and see how this works. Because you will get one like this in exam. Now unfortunately, that is way easier. This one, where over here, current goes in through the diode, around and back. Then it goes from neutral through the diode and back. That is exactly the same as in there, around and back, and then in the opposite direction, in there and back. Any questions? Will you practice this one? Guys, I guarantee in the exam, at least one electronic question you can get right. Right. Three-phase rectification. If I put three-phase in, everything below the line gets swinged up. Operation, only think about two lines. 1 and 2, 1 and 3, 2 and 3. Look what I do. 1 to 2. 1, go through diode 1, through the load, and it goes back to line 2, which is diode 5, back to line 2. The next one, I go to line 2, through diode 2, go to diode 6, up to line 3. So you can work out which one you want to work, just to show you how does it work. Now guys, here comes the thing. So you put 50 hertz in. For full wave rectification, how many hertz are you going to get out? What is 3 times AC? What was that previous one? 52, 100. What is 3 times 100? 300 hertz. So remember, if I give you, oh shit, the thing doesn't work. If I give you 4 diodes, it's 50 in, 100 out. But now I give you 3 phase. It's 3 times 100. So that becomes 300 hertz. Right, guys? Happy with that? If you half it, how much are you going to get? 150. Now, guys, that has been asked in the exam. In a 3-phase system, if you put 50 in, how much you get out full wave? If you put 50 in as half wave rectification. So guys, if I get rid of the 3 bottom diodes, you're going to get 50 hertz. But then you're going to have a pulsating 3-phase, not a ripple 3-phase. Right, guys? We're nearly there. We got only 3 more circuits to do. All right? Firstly, you all agree that AC can be rectified by an inductor. Try again. DC, ripple, can be rectified to make a straight line. To do that, you either use a resistance, capacitive, or inductive circuit. And what you then do is you get a straight line. So what it does, every time it switches on those waveforms, the cap in that will discharge very slow, and when the voltage comes up again, it will pick it up. So technically on an oscilloscope, you will only see a straight line. Got it? That's nice to know. The reason I say this, I believe in the exam, they give you a sine wave and they ask you, which of the following waveforms will you use if you put AC in and you rectify it, or you put AC in and you have pulsating DC, or you put AC in and you get a full line DC. Have a look at the last questions of my semiconductors. It took me ages to draw it. Gentlemen, ladies, it's asked in the exam. Go to my workbook and look at them. Right, guys, you're sitting on that gold mine. Just use it. Right, guys, a Zener. A Zener is the only diode we connect up in the opposite direction. So a Zener, we connect up in reverse bias. So that means as the voltage goes up, the Zener will divert the voltage and current flow, so you will always have a constant voltage across a load. Many, many moons ago, could you remember the cars? As you rev them, the lights goes brighter. So they put Zeners in it, and now the voltage is constantly the same. Just to give you an example, they use other stuff as well, but a Zener is one of the devices. So, the conclusion you need to know here, a Zener is not connected in a forward direction. A Zener is connected in the reverse connection. So if you look at my picture, can you see the positive goes in? The Zener is always in the wrong direction. That's how it operates. Right? This is a SCR circuit. Now guys, I'm going to make this as simple as chips. I want to ask you this. What do we call this device over here? This is a variable resistor. What do we call this SCR? I know this is silicon control rectifier. Can you see there's a diode? Can you see there's a cup? Right, guys? What's the purpose of this circuit here? Right, guys? The SCR, and you got a load. The load will not work till I put a voltage on the gate, right? A SCR will only switch on when I put a voltage on the gate. The variable resistor will determine how long the cap will take to charge. Once the cap is charged, allow then only current to flow to the gate, and then only the motor switch on. Make sense? Now, guys, in the exam, they'll ask you, what's the purpose of the variable resistor in the circuit? There's my answer. The variable resistor will determine how long the cap will take to charge. You guys with that? Cool. Right, guys, once the cap is fully charged, then current will flow through the diode, which will switch on the gate, and then current will flow through the SCR. Now, guys, look carefully what I'm going to do. I'm going to give you a picture. I take this resistor and I put a lot of resistance on it. Look how long it took to charge. Once the cap is charged, it switches on the switch, SCR. Then there's nothing flowing because current can only flow in one direction. It cannot flow back. Does that make sense? Now, A is the time it took for the cap to charge. B is when it's fully charged and it switches on the SCR. That's it. Once the SCR is switched on, it will switch off because the current now flows in the opposite direction. What happens here? Nothing. Reason for that is when it flows back, the SCR stops the current flow. It's like a diode. Then it starts again. So you will only see a ripple value from it. Now let's change that resistance to a little bit more, 50%. Let's change it a little bit more. Let's change it a little bit more. Can you see that the bottom picture, the resistor is now basically charging the cap all the time, every time you switch it on. So you all agree that this resistor will determine how long it takes the cap to charge before it switches the SCR on. Now, gentlemen, ladies, that is a very big question in exam. They can ask you the purpose of that, or what they then do, I believe, I heard, that they put this in different orders, and you must say the order in which it operates. So let's follow again, last time. The variable resistor will determine how long the cap will take to charge. Once the cap is charged, yeah, the diode will switch on the SCR. And when the SCR is switched on, current will flow through the load. You guys got it? Now, in the back direction, it switch off because it cannot flow beyond the SCR. That's why there's nothing in here. Cool? Right. Let's try his uncle. This uncle is a strong bugger. This is the one we always used to use for little dimmers in the bedroom. You know the one with the pot you turn? That is a circuit in it. So instead of having a diode, I put in a diode, a diac. So instead of a SCR, I put in a triac. Now look again. Can you all see one direction? What does that tell us? DC. Both directions. What is both directions? AC. Now guys, what does a variable resistor do? It will charge the cap. It will determine how long the cap takes to charge. You guys happy with that? Once the cap is charged, current will flow through the diac, switch on the gate of the triac. Once the triac is charged, current will flow through the circuit. Take note. I'm going to say that again. The variable resistor will determine how long the cap will take to charge. Once the cap is charged, the diac triggers the gate of the triac. See there? The diac will switch on the triac. Once the triac is switched on, current will flow through the triac. Right? Now, in the opposite direction, current will flow through as well as through the cap. That variable resistor, and take note, it will not switch on yet because the gate must be made first. Once the cap is fully charged, what does it do with the gate? Switch on and it works. And then look at this waveform. Can you see it? Now it switch on the bottom part as well. Look at that picture. Look nicely at this one. Compare with that one. Can you see that the bottom part's been taken away? Where a triac diac cuts the bottom parts as well. Now, gentlemen, ladies, many people get questions from this. Triacs, diacs. Now, quick question, quick fire. What's the purpose of the variable resistor? To charge the capacitor. Yeah, it depends how long it takes to charge. Once the cap is charged, it switches on the what? The diac. And the diac will switch on the gate of that. That's it. It works. Now, the variable resistor will determine how bright the light is. In other words, how long it takes to charge. And gentlemen, and ladies, that happens very quick. Very quick. Remember, it happens 50 times a second. So, that's important. Now, guys, at the bottom one at 100%, is it true that it charges all the time? It basically works all the time. See the bottom one at 100%? That means your light or your motor is running at full speed. Now, guys, could you recall I said to you that if you change the voltage, you take parts away, you change the voltage as well. So you don't just change voltage by putting one diode in, but you also change voltage by make it operate slower. Go to 50%. What's 50% of 230 volts? 150 volts. Now, all what you do, you take voltages away. So at 75%, you might get, what, 200 volts? And at full load, you get 230 volts. So what it does, it reduces the voltage on the load. So what it does, voltage regulates. It regulates the voltage. It tunes the voltage. Happy with that? Right. It's not too hard, guys. Heaps of you guys will get this in exam. Some people will not get it. If you get it, I love it. I think it's quite easy. Now, guys, please try to do this for homework. If I look in this class in front of me, there's 2, 4, 6, 7 of you guys. 5 out of 7 will not do it. You guys will wait till 2 weeks before you sit the exam. I know that. Online, there are in total 32 of you guys. I hope that at least 2 of you guys will do it. We're nearly there. The last topic. The last one. Hey. Right, the last topic is called a transistor. What is a transistor? A transistor is an electronic contactor. Electronic contactor means a contactor which will determine when to switch it on or switch off a circuit. So, electronic device. Sorry guys, I just want to let some people in. They sneak home and they got caught and now they have to come back. Right. Now before I do a transistor, and I'll tell you how the switch works. Can you all see the symbol? The transistor has got a little arrow. That tells you where the N is. So it's NPN. See there? PNP. Right. Every layer creates heat. So there's 3 layers. Can you see that? So a transistor's got 3 layers. It's got negative and positive. Now let's look at a transistor. You need to put a voltage on the base. Once you put the base voltage in, the internal resistance of a transistor will become less, and then the big current will flow through the collector and emitter in that direction. And if you look at this one, this is a PNP. All what you do is you allow current to flow in the opposite direction. See there? All what it does is it changes direction. That's all what it does. It's exactly the same thing, just in the opposite direction. All right? Now, what you're going to get in the exam about that one. What is the purpose of a transistor? A, does it rectify the voltage? Or is it like a switch? Switch stuff on and off. Now, there's one more thing it also does. It amplifies the signal. So that transistor could be a multiply with 5 or multiply with 10. So if you put 1 amp in and it multiplies with 10, how many amps will flow in the other part? 10 amps. So it's also like an amplifier. So guys, the transistor, unfortunately, you'll get a couple of questions, but the most common question is this symbol. The symbol of an NPN or a PNP. Now, the last question on all the semiconductors I did, how do you keep them cool? Do you put it in water or do you mount it on an aluminium block? Have you guys ever heard about the heat sink? Heat sinks? Right. Guys, another way to keep it cool, if you listen to my overhead projector, hear that fan running? Cool air over it. Now they can ask you, how do you keep electronic stuff cool? You all agree we use heat sinks or fan cooling. Right. Lovely. So guys, any questions? What's this hard? What's very important for you guys is to go and practice this and practice this and practice this. So, if you struggle, you must ask questions.